I saw this post yesterday on Reddit and I really wanted to give it a try. I thought this was really cool. It says help with noise. Stoli232 on Reddit says, I found this image and it looks like it was generated using noise. I've tried a bunch of different variations on the noise function and I've come up with some very interesting images, but can't seem to achieve anything close. Here's where I'm at. So yeah, this is really cool. This looks like 3D, like smoke kind of to me. And it's just like super interesting. It's got that little topography kind of thing going on here with the lines. So you can see there's some consistency, you know, to as this is rotating around what's happening here. There's a discontinuity at 0 in this code. So let's take a look at the code here. And somebody in the comments already called that out. But there's still not a solution for this. So let's just take a look at what this code does. That's cool. So it's drawing it out radially this way somehow. And that's probably where the discontinuity is coming from, because this is happening independently of this. So there's nothing to control to make it smooth. So I took a shot at this and worked on it for a little while. And then I decided to kind of cheat and just copied this image and looked it up to try to get a hint. And I found what I believe is the original creator of this, Simon Russell, motion designer. He does a lot of pen plotting stuff, it looks like, and super cool. And then right here it is. This is called Noise Flower. So this is really a work by Simon Russell called Noise Flower, and it's done with a pen plotter. And it's really cool. And you can see here, here's the hint. It says this plot, this plot uses one continuous line that spirals outwards. As it does so, it becomes increasingly affected by a noise field. This took the plotter 5.5 hours to create and traveled a distance of 167 meters. So that's insane. And I do wonder if the plotter was actually computer controlled and like the simulation happened in real time on the plotter, or it was known, you know, like done with code a couple times just to make it see if like it looks good and then sent to the plotter. But if it was just done in real time with the plotter, that's like even more cool. Okay, so here's our hint. This plot uses one continuous line. This is like really tiny, so maybe I'll make this bigger. This plot uses one continuous line that spirals outwards, and as it goes further outwards, it becomes increasingly affected by a noise field. Okay, so a noise field. So here's what Perlin Noise looks like. The function for 2D Perlin Noise, it basically gives you a topography, a smooth topographical landscape sort of. So that's what we're seeing here. We're seeing the topo lines being drawn. You can see that the lower numbers are blue and the higher numbers are a brighter green. And you can see the little hills and valleys and contours of this landscape. So Perlin Noise gives you this kind of thing, this kind of a landscape that you can move over, and then you can select any point. You can give it an X and a Y coordinate, and it'll tell you what the value of that is. So you can think of that as like the height at a certain point on the landscape. Okay. So the code that we have from this Redditor who asked this question does use Perlin Noise. Noise is the function built into p5js that returns a Perlin Noise output. So what they're doing is begin shape, end shape, and then they are they're doing var x and y, center x, center y, so I assume that's just the center of the canvas, and then they have a default radius of 40, plus cosine of I plus radius times cosine of I times the noise factor. Okay, so here's the difference. What they've done here is they're using the value of the noise factor, to offset the radius. So they're changing the total radius of the drawing radius using the noise factor. And the differences here is between just the having the topography affect the value directly, and instead using a Perlin noise field, which is different. So a Perlin noise field is, what you do is you take these values, and these values control the rotation of a vector at that point. So I checked out Dan Schiffman's video on this, and that helped as well, seeing, because I saw this and I said, you know, this looks more like what we're going for. It looks more like stringy smoke than it does a topography. So the problem with this code is this is changing the radius according to the topo value, like so. So the radius is default to 40, right? And then as it changes, it's changing based on the value of the Perlin noise. What we want to do instead is go out by our radius and then change by the whatever the vector at that the vector field is telling us to do. So we're going to offset by that amount. So it'll be different things at different points, right? So if we have it like this, and then the vector says to point this way, we're going to offset like that. So you're offsetting by the noise field, not just the noise value. Okay, so that's pretty much it. Like, that's the big missing piece for this, as well as you want to spiral out. I'm not sure exactly how it's, I didn't look at this code too closely, but it's all going at once. If you spiral, you're going to get rid of this discontinuity. All right, so I have some code here, and it looks like this. And I think this looks a lot closer and definitely on the right track. There's a ton of tweaking to be done to make it, like, you know, look closer and more, and I think that's where like the art comes in. But I think it's like getting there. I also think this is a absolutely massive number of iterations. Remember, it said it took 5.5 hours of plotting and traveled a distance of 167 meters on the plotter board. So I have this cranked to, I think I had it up at 1 million at one point, but my computer was like, it kept crashing. 100,000, or no, yeah, 100,000 basically iterations. But you can make this more and see. I guess I'm safe to, I can go up a little bit more here. Yeah, so we get this kind of behavior. All right, let me explain how I did this. So remember, our goal is one continuous line that spirals outwards, and as it does, it becomes increasingly affected by a noise field. So we're not just changing the overall radius by some multiplication factor determined by the value of that noise field. We're displacing by the vector determined by the noise field. I should have said noise value here. So we're not just displacing by the noise value, we're displacing by a vector determined by the noise field. So that's really the fundamental difference, is the noise field versus just using the noise values. To create a noise field, you take the Perlin noise values and you control the rotation of a vector based on the values. The Perlin noise values are values between 0 and 1. So you just determine the rotation of the vector at that point using those values. I hope that makes sense. I may try to explain that more in a second. So let R equal 40. This is going to be our starting radius since we are spiraling outwards. We're going to start at some value so we get some center circle. So if we want to spiral outwards, it's going to be something like this, like line of, just to see what's happening, 0, 0 to R cosine of frame count divided by 100, R times sine of frame count divided by 100. Okay, and I'm just gonna translate the entire thing to the center of the screen by doing width divided by 2, height divided by 2. And then we can see this. So I can make it a little faster. We want to spiral outwards. So as this goes, we want it to spiral outwards, so we could say like R plus equals 0.1. So this is the idea. If we want to visualize this right now, we could draw, instead of a line, we could draw a circle at that point with a little radius, and then we can see we're getting some spiraling effects. Sweet. Okay. And we can bump this up maybe to, there we go. Okay. So that's the idea. We want to spiral outwards, and as we spiral outwards, we want it to be increasingly affected by a noise field. So let me try doing that. So let's do this. Boom. Spiraling outwards. I'm going to make this like really small, actually. Just 1. Cool. All right. So as we spiral, we want it to be affected by a noise field. I'm just going to make the stroke weights 0.2 and actually fill 0.2, and I'll just do no stroke. Okay. Sorry, I'm getting hung up on small details. Oh, sorry. All right. What's going on? There we go. Bear with me. I just want to have a good starting point before I start trying to mess around with the other factors here. Okay, so this looks cool. Yeah. All right, nice. So we're spiraling. And now I slowed it down a little bit so it's not just going to be out of control. So we want to affect this by a noise field. So as it gets further and further away from the center, we want the noise field to have a larger and larger effect on it. And that's how we're going to get this like behavior, hopefully, of spiraling out and getting crazier and crazier. Okay, so what we can do is affect this by noise. Boom, boom, boom. So we could just say this and then plus noise of our X and Y position. So I'm going to say let X equal R cosine of frame count, blah, 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 and let Y equal R times sine of frame count divided by 50. So now this is our X coordinate and this is our Y coordinate. And then we're going to grab the noise value at that X and Y coordinate. Okay, so plus the noise value at that X and Y coordinate. So this, again, is just a small value between 0 and 1. So if I do noise of X, Y, and console log it, then we'll see that this is just a value between 0 and 1. So that's why we can't even notice what's going on. So we'd want to have something called dr, and dr, the like delta r, will be the how much we're going to vary r by. So if we're just having a dr controlled by the noise value, then we can say this is noise of xy times like 20 or something. So then we can say dr boom, and now we get a noisy spiral. So that's kind of interesting in itself, maybe. I wonder why it's, oh, we're visualizing the Perlin noise. I think the topography of the Perlin noise is coming out in the way this is shown. Why is it always the same? Oh, hang on. No. dr times cosine of the angle. And dr times the sine of the angle. I forgot that. Okay. Yes. Okay, so now we just have this noisy, very noisy spiral. And it's very noisy, right? And the reason it's very noisy is because x and y are huge values. These are like 40, 45, you know, increasing to like 47. So let's make these smaller, because if you're grabbing, Perlin noise is smooth locally, right? But if you're grabbing values that are over here, over here, over here, at that point it's just random. But locally it's smooth. So we need to get more local. So we need to decrease, there we go, our values. Now we can start to see it's following some sort of a smooth topography and getting values from a nice smooth Perlin noise graph. All right, so this is where our friend Stoli232 got to, and I believe that is the problem, was they were modifying the radius like I am now. They did the default radius of 40 plus this radius factor, and they did cosine of the same angle, right? So all they're doing is affecting the length of the radius based on the noise field. But that's not what we want to do. We want to offset, we want to move by the default radius and then offset by the field vector. Okay, so let's get a field vector, the field vector from the noise. So we're getting the noise value. This noise value is between 0 and 1. So instead of dr, a change in excuse me, the radius, we're going to change the theta value. So I'm going to say, and d theta is misleading, so I'm just going to say call this theta, which is the rotation of the vector in the noise field. So we're going to get the value of the noise, and then we're going to multiply that by 2 pi. And that'll give us a value between 0 and 2 pi. It'll give us a, you know, orientation. And then this is what we are going to do. And then I'm going to say let v, for how much we want to displace, we'll just have it be, well, we know we want it to increase with r, right? So we'll do r minus 40. So when at the beginning it'll be 0 because r starts at 40. And then as r goes beyond 40, this vector value, this is really the vector magnitude. This vector magnitude will increase. And so we're starting off when we're here at the first time, when the spiral first starts, we want basically, no offset. But then as it spirals like out here, we want a big offset. So the magnitude of that vector we want to increase according to r. So we'll just do this times like 20. Okay, and I didn't even do anything. So hang on, dr plus vmag, the vector magnitude. And then this is the key. Instead of using the same angle that we used for our initial displacement, we're going to use this angle theta, which is the angle of the vector in the vector field at that point. Okay, and now stuff is happening, which is cool. I think this is just way too big, so let's try to make it like this. And it's still way too big, so we're probably going to need to be dividing by something. So we want a few rotations of basically a perfect circle, and then we want it to start to get a little wild. All right, starting to wobble a little bit. I'm going to make a speed value here because this is a little boring. Speed. And I'm just going to replace all these with the speed. And I can make this faster, hopefully. Oy. Okay. So yeah, once you get it, I think I have it, but now it's like a matter of, tweaking everything and making it to get the results to be nice, like you want them. Also, when you do this, you're gonna have this all be done in a for loop. So it's just gonna load and boom, show you the entire image at once. It's not gonna draw it out like this unless you want it to, which is kind of cool, but it's a little boring in the beginning. Now it's starting to get interesting. Now we got some stuff happening. Right, because now the radius has increased quite a bit. So this value of the Vmag is larger. So the vector that we offset by is larger. Okay. All right. Apologize if this is boring. Well, it's kind of exciting. While that's running, I'm going to try to encapsulate this functionality into a for loop so that we can, rather than having to sit and watch it draw, we can have it do everything at once. And while I'm at it, I'm going to make it a begin shape, end shape. So it's a line and not a bunch of circles. So begin shape, end shape. And in here, we're going to have a for loop. For let I equal 0, I less than. We'll start at like 1,000. We'll make that bigger as we go, as we get confident that we're not going to crash the browser. All right, and then let's like put all this in here. So let's just put all that in there. There we go. This should work, right? Vmag circle. Okay, right. So instead of circle, we're going to do vertex. And it basically takes the same arguments, an x and a y location, and it doesn't need a radius because it's not drawing a circle anymore. And there we go. All right, and then we're going to end shape, and then we're going to no loop, which is something that I forgot about until I saw this Redditor's code, so that's cool. Okay, let's try it. What row? Oh, did something. Whoa. Ah, no stroke was called. So we need the opposite. We need stroke this time and no fill. No fill. Yeah. This looks good to me, guys. Just kidding. Okay. Oh, I'm not even using I in any fashion. That's why. Frame count needs to replace with I. There we go. Yeah, sweet. Okay. Awesome. All right. Does this look like this? No, not quite. But I think it looks less like, I mean, I'll post this code in the description, so if you want to just look at these results that I got. It takes a lot of tweaking to get to this point, so it was a lot of, you have to play with like the noise field, right? Because you can vary S, and that'll affect how detailed the noise field is. I realized I shouldn't have used S in that position, but okay. So also stroke should be stroke weight should be 0.1 or 0.2 or something. Stroke can just be 0 for black. Yeah. Okay. And then you probably want this curled tighter to be denser at the beginning. So to do that, you can change this, how much you're changing R by. Look at that. That's cool. So you could have it be like super dense in the beginning. And then if you want to do something like this. There we go. And I do agree that I think you do want it to be nonlinear. Oh boy. I think I blew it up. Stop. So yeah, if you look at my code, I have all these little parameters set in the beginning, so you can kind of tweak things. Changing D will change like how dense the noise field is. So if you wanted to make it like 50, it gets crazier faster. And if you want it smoother, you could go higher. And then there's less activity. but tweaking or getting this to the point where it looks nice and has like the right amount of turbulence. Did I break this? Yeah. Right. Okay. So now you can get sort of like some values. It's tricky because changing one value changes the others. So if you like get something dialed in, like this value here, to something that you like, if you then go and change something else, it can affect the entire thing. So, getting this dialed in to a reasonable value, and then that's where the art comes in, It's a bit of an art as well as a science. That's why I was questioning if the person that made this, probably like figured out in code the parameters ahead of time and knew it was going to look cool. And then maybe they did the pen plotter in real time. But yeah. Whoa. See what I mean? You change one value and then it all just kind of explodes. But that's nice. We're getting that kind of behavior on the end. So we need this to be a little bit bigger. Maybe even like 3. Can get crazy. Whoa. Yeah, so it's interesting. I think it takes time. Like I believe this is the same code as this now. I will post both of these in the description if you want to play around with it. But again, the main thing was using a vector field generated by Perlin Noise rather than using the Perlin Noise value itself to change the total radius. Thanks for watching.